Hello. Alright, this is going to be the second video in solution stoichiometry. I'm going to go a little beyond just your general solution stoichiometry problem. As I showed you in the last video, I showed you how to find your limiting reactant, how to use volumes and molarities to find the moles, and how this problem is very similar to problems that we've done in the past. So what I'm going to do in this video is just kind of show you how the table can be useful and some of the things to watch out for when you're doing solution stoichiometry problems. Okay, so where I left off is I had the limiting reactant, and what I found was that this is the amount of potassium chromate that I had to use in the reaction. So therefore, if this is the amount that's used to react with all of my limiting reactant, the silver nitrate, I can quickly figure out how much is left over. Okay, so if I do the calculation here for the 0.0400 moles, and I subtract out the 0.0375, that's going to leave me with essentially 2.50 times 10 to the minus third moles of potassium chromate. So I can quickly just take the 0.0400, which is my number of moles of potassium chromate starting out, okay, and what I could do is just subtract that out from the original, and I would end up with 0.0025 moles. And I just move the decimal over just to write it in scientific notation because I do not like having more zeros. As soon as I have two zeros in here, I write it in scientific notation because I tend to make mistakes with the zeros here. I don't like to write them out. If I miss the decimal, it's a nightmare. So as soon as I see 0.00, I right away try to convert to scientific notation. Okay, so anyway, so this is the amount of potassium chromate left over after the reaction goes to completion. That is, all of this goes to zero. Now over here, I can figure out how much of the silver chromate I have, which I believe I did that in the last problem. I'm going to quickly calculate that. It's really, if you look at this problem here, another way to solve these things, if you're using the table, is that this minus 2x has to be equal to 0. So the 0.0750 moles minus 2x has to be equal to 0. So therefore 0.0750 moles is equal to 2x. Divide them both by 2 and you can get your x, which is going to be essentially 0.0350 moles. Okay, so therefore if this is 0 plus whatever x is, this has to be 0.0350 moles, and over here my 0 plus 2x would be the same as this problem, just backwards, so therefore 0.0750 moles. Okay? Alright, so now we got that established. We have all the moles that we have at the end of the problem. I'm going to show you what they tend to do sometimes with these solution stoichiometry problems. What we have here is you're going to think about what we're doing here. We're taking this solution here, okay, which has the, let's just draw that better. Okay, so we have a solution here that has the silver nitrate in it. Silver ions plus your nitrate ions. And we're going to combine that together with this solution here. And that has your potassium ions and your chromate ions. Okay, it's a good idea to think of ionic compounds. If they're aqueous, ionic compounds, you're going to think of them as ions in solution just kind of floating around. And what I'm going to do is I'm going to combine these together. Now think about this. Hold on. I have 150 milliliters. Over here I have 100 milliliters. So if I combine those together, what I'm going to have is a solution that now has silver ions, potassium ions, nitrate ions, and my chromate ions. And my total volume afterwards is now going to be equal to 250 milliliters. Very important to realize. Why? Because of the fact that solutions change concentration as the volume changes, right? Because it's molarity, and molarity is moles over volume. Well, if this is what molarity is, and I'm changing the volume from 150 to 250, I'm changing my molarity. So be careful with this, okay? So think about what's going on. Now, in this problem, the silver comes in contact with the chromate, creates that solid, right? This is what's making that solid substance. So at the end of this problem, if I look at this, what I have, all of the silver ions are no longer aqueous, are they? All of them are now in the solid phase. So what I want to do is redraw this part here, okay, so we can make this look a little bit better here. Let's get rid of the beaker here and draw another one. Okay, so what's going to happen is I'm going to have in this beaker, okay, still going to have 250 milliliters of solution, but I no longer have silver ions. They're now gone. Okay, so the silver ions are gone. I still have potassium ions because they're now still aqueous. I still have nitrate ions. They're still aqueous. My silver is gone. That's now a solid sitting at the bottom. So let's change the colors here. Since it tends to be a Since chromates usually are yellow, let's go ahead and put a yellow solid down here. It's kind of hard to see that, but you hopefully get the idea. The yellowish orange color. Okay. So what I have here is a solid substance setting at the bottom of my beaker. That solid is silver chromate. Okay. Now, if I think about the after part of this reaction, though, not all of the chromate is gone. I still have some of that chromate in solution. So be careful with that. Make sure that you're aware that the chromate is still in the solution. So therefore I have CrO4 2- in solution. So I essentially have 3 ions still remaining in solution, and that is very important to keep in mind. A lot of students don't think of it that way. They think of it as reactants and products. They think of the reactants as the beginning, the products as the after. Okay? We're going to think of it as after right here. So you're going to remember that this is still present. It's a very good way to visualize the problem, is to draw out these little beakers with the ions in here so you can kind of get a visual as to what's going on at the microscopic level. It's hard to picture this if you're not being careful and kind of planning the problem out. So, what's the concentration of the chromate ions at the end of the reaction? Okay, what I want to know is what's the concentration of chromate ions. So I want to know what's the molarity of chromate. Okay? Of those chromate ions. So to do that, if I'm looking for the molarity, I'm looking for moles of chromate ions over my volume of solution. So my volume of solution, as we said earlier, is going to be 0.250 liters. Because I'm doing molarities, it's going to be in liters. My chromate ions, well, I have some here and I have some here, right? So if I have the chromate ions here, I'm going to do the 2.5 to the -3rd plus 0.035. That's going to give me 0.0375 moles of chromate ions. Okay, just to backtrack that again, if I look at the problem, I'm looking for the chromate ions. I have chromate here, and according to this, I still have them left over at the end. And I have chromate. That's a solid. Notice what I just did. See, good thing I did this, because I noticed that that's a solid. Those are the ions that are no longer in solution. So let's cut this part here. Okay, and we're going to just put 2.50 times 10 to the -3rd moles. Okay, good thing I caught that. It's, again, going back and checking the problem, double checking things is definitely a good idea. So solid here, aqueous here. Those ions are no longer in solution. So I'm just looking at this portion here if I'm trying to figure out my ions of chromate. Okay, what I got confused with was what I was thinking of the potassium ions, because there's 2 sources of potassium ions. And this can get a little tricky, so I'll show you those in just a second. So if I do this calculation, I can get my concentration, 2.5 to the -3rd, divide that by 0.250, and I end up with a concentration equal to 0.0100 molar. 3 significant figures back in the problem, and that would be my chromate ions at the end of the experiment. Okay, so if I look at the beginning of the experiment, my potassium chromate ions were about a 0.4 molar solution in 100 milliliters. So it clearly went down at the end of the reaction because I used a lot of it to react with the silver. Okay, and the silver ultimately goes to 0. If If I were to find the potassium ions, there's a couple ways to do it, but if you want to just kind of follow what I did before, what I would do is I'd look at the formula. Now, here's the trick. Because this is a K2Cr4, each of these moles has to be double for that potassium right here, right? Because I have two potassiums. So therefore I would have to double that one for the potassium ions. Now, it's a 2 here, but we already took that into consideration down here, so we don't do that here. The formula is KNO3, so therefore it's going to be the same number. So if I were to do that problem, I would do 2 times 2.50 times 10 to the minus third moles, right? And I'm going to do that for this part here. That is going to be this portion here, plus this portion here, 0.075 moles. All of that's going to be over, hopefully you know what volume, 0.250 liters. And then I can solve this. Now again, this portion here is going to go down here. Okay? Double check aqueous, aqueous, potassium, potassium. So we do that calculation, 2.5 minus third times that by 2, add that to 0.075 and divide it by 0.250, and I end up with a concentration of potassium ions of 0.32 molar potassium ions. Okay? Alright, so just to check that one more time, if we look at the original solution of the potassium ions, it was 0.4. It went down because I did dilute the solution down a little bit. It went from 100 milliliters to 250. I didn't do anything to those potassium ions. They didn't do anything in the reaction. The total number that I started with is equal to the number that I have at the end. So if I just do a little check here, okay. Anyway, we'll kind of get back to that a little bit later. So anyway, so there's the final calculation of the solutions afterwards. Hopefully you can see why this BCA table can be useful for a complicated problem like this, where we're analyzing the results after a reaction. So hopefully you need to watch it again, ask some questions in class, but that should be pretty much it. Thanks.